All right, ladies and gentlemen, I'm just going to be walking through these entire slides um, that are going to help you to calculate the electric field or net electric field between two charges. The reason I'm going to walk through the whole slides is just because this can be a little bit more complex of a concept. So kind of walk through it together. So today you'll obviously be going through these slides, whether it be on your own or watching this video. Complete the day 3 exit ticket by 2:30 today, and then also complete the day 3 assignment called electric fields. And remember, when I say complete that day 3 assignment, um, that is just going to be something that you don't turn in. It's just for your use. So taking a look at just electric fields in general, it is a force felt by a small positive test charge. So when we use a test charge, or sometimes called a point charge, it's a positive charge. So like if I were to place a small point charge right in the middle here, it's usually just represented by a dot, sometimes just a small positive charge. But since that is a positive charge, what that tells us is you see all these what we call field lines here on the positive are all pointing away. And that's because if we are using a positive test charge, well, like charges are going to repel each other. So that point charge or that test charge is going to get repelled away. And then for our negatives here on the other side, it is going to be attracting it. So for that positive test charge, it would be going this way for the negative. So you're going to have to be able to calculate the electric field when you were given just one charge, and then we're also going to look at calculating the net electric field as well. So, oh, that is not what I wanted. Let's clear this. So let's take a look at, in order to calculate the electric field, there's two different equations we can use. There's E is equal to force divided by Q prime. Sometimes it's called Q naught, where Q prime or Q naught is just our test or our point charge measured in coulombs. Force is newtons, and then E is our electric field, which we are measuring in newtons per coulomb. The other way that is also pretty commonly used is instead saying that our electric field is equal to KQ divided by R squared. So K, remember, is that Boltzmann constant, and then Q is just your test charge or your point charge, and then R is your, or sorry, Q is not your test charge, but Q is going to be the actual charge of whatever it is, whatever field that you are dealing with. And then R is going to be the radius between them. In reality, that ends up just really being the distance between them. Okay, I just want to kind of relate this a little bit to force and kind of see how this would relate to force. If you think of this equation over here, and if we think about that in terms of our force relating to acceleration, right? We know from first trimester, or the first half of this class, our acceleration was equal to force divided by our mass. Okay, or F equals ma, right? So if you want to think about it this way, it can kind of help you to understand what exactly electric fields really are solving for. We have our force measured in newtons, and then if you want to relate mass basically to the charge, and then relate your acceleration to the actual electric field itself, that can kind of help you, because let's say I were to have a positive electric field, and here's a point charge over here. This point charge right here is going to be being pushed away, right? Just like we said before, positives are going to repel those positive test charges. All right, and the amount of newtons per coulomb, or the electric field that it is being the magnitude that is being pushed away with for that number, the higher that number is, the you can think of it, you can relate it to acceleration, thinking, the faster it's moving away. Okay, if that kind of makes sense. All right, so just to kind of relate that a little bit to our force equations from the first half. All right, so let's take a look at an example here. I don't know why it keeps doing that. So this is just an example of using your just electric field equation. We're not moving on to net electric fields yet. What is the magnitude and direction of the electric field 1.2 meters above a positive 4.2 times 10 to the negative 6 coulomb point charge? Okay, so what we are going to have is you have, one second here. All right, you'll notice sometimes that I go up here into my top right hand corner here and I just kind of pause the video. And the reason for that is just so that I can kind of get my thoughts straight and make sure that I'm not going to give you guys false information or screw anything up. So what we're going to be doing here is we are saying that we have this is our point charge of, this is that positive 4.2 times 10 to the negative 6th coulombs. Okay, and I want to know what is the magnitude and direction of the electric field. So remember, this is a positive, so all of our electric field lines would be pointing out. And what is magnitude and direction of the electric field? That is 1.2 meters above that point charge there. All right, so we're going to go back to our equation. Remember from this slide here, we said that we had E is equal to KQ divided by R squared. All right, and that is the equation that we are going to be using. Oh, it does keep my stuff there. That's nice to know. So we're going to use that equation. E is equal to KQ divided by R squared. All right, and the reason we're using that equation is just due to the information that we are given. We are given 1.2 meters, which is a radius, and then we are given 4.2 times 10 to the negative 6, which is a charge, or Q. We can't use this equation right here. Can't use that one because we are not given a force in this particular instance, so we are not able to use that equation. Okay, so let's go ahead and just plug everything in here. So we have E is equal to K. I'm not going to write out K again. Hopefully you guys remember. K is equal to that 9 times 10 to the 9th. That's that Boltzmann's constant. And just so you guys are aware, if you ever are seeing that some of my answers are just a little bit off, it's because I might have used what is the true Boltzmann's constant. The true Boltzmann's constant should actually be 8.99 times 10 to the 9th. For simplicity's sake, I just had us round it to 9. I just figured that would be a lot easier for most of us. It makes it, so when you get some answers, you might notice that my answers are just a little bit off. All right, that's okay. All right, so we have K times that Q charge is that 4.2 times 10 to the negative 6 coulombs. And then we are going to divide that by the radius between them squared. So 1.2 squared. All right, and what you should end up getting is you end up getting 2,622, 26,220.8 newtons per coulomb. And it asks what is the direction of the electric field. And since we know that this is giving off this is a positive point charge, and it is going up, or it's going away from the 1.2 meters away. We are going to say that the direction is going to be up. So 26,220.8 newtons per coulombs up. All right. You can go ahead and try it on your own. I wish it would stop doing that. You can go ahead and try it on your own. I did already put the answer there so that you can try that on your own and see if you get the correct answer. Here's some field interaction lines just to kind of give you a show of how charges work and interact with each other. These lines here that are drawn are imaginary lines that we can't see. Obviously, between, if you want to think of it as something like a magnet with a positive and a negative, these are lines that we can't see whether they're attracting or repelling away from each other. And they always flow from positives, or our field interaction lines always are going to flow from positive to negative. That's why you're noticing that we have the arrows pointing away from the positive, and they are going towards the negative. All right, and the last thing we're going to do here is we're going to calculate the net electric field. All right, so basically what we're going to be doing here is we know that we have one charge over here, Q1, that is 10 to the negative fourth coulombs. And then we have another charge over here, Q2, that is 10 to the negative fifth coulombs. And we want to know what is the net electric field at a point midway between these charges. So right in the middle, so it looks like they're 2 meters apart from one another. So the radius then would be 1 meter for each of those. At that point, right in the middle, which way is this thing going to be moving? Okay, well, if you think about it, we have both of these charges, Q1 and Q2, are both positive. All right, they're not negative charges, they're both positive. So what that tells me is that both of these are repelling away any test charges. Okay, so pushing away, all my field lines are going out. So what that means, if there's a charge right in the middle, it's going to be going either to the left or to the right. All right, and that's what we have to figure out. We have to figure out the magnitude and which direction that it's going to be going. So basically what we need to figure out which one of these, Q1 or Q2, is essentially pushing it more, so that we can determine which direction it's going, either to the left or to the right. So in order to do that, what we need to do is figure out the electric field for each one. Just think about it individually. So we can just go ahead and we'll figure out the electric field for A first. That was sloppy. And we're going to use that equation that was E is equal to KQ divided by R squared. Okay, so we have that K constant. And I'll continue to write this over here just so that we don't lose track of what that K value is. Okay, so K multiplied by my charge on A is 10 to the negative fourth coulombs. And I guess if I wanted to, and I'll just erase this really quickly just so I can write that properly in scientific notation, it should be 1 times 10 to the negative fourth coulombs. And then we'll divide that by the radius between them, which in this case is just 1 squared. So that's essentially going to mean nothing. All right, so we solve for that, and we end up getting 89,000. Oh, I keep doing that. Sorry, 899,000 newtons per coulomb. Okay, so that we have, this charge is, I use the word pushing, is pushing, essentially pushing with 899 899,000 newtons per coulomb of an electric field. So that's EA. All right, and let's switch to a different color here. And now we will solve for the electric field of B, doing the same thing, K times 1 times 10 to the, this is -5th coulombs. And we're going to divide that by the radius between them. Once again, since we're dealing with that charge right in the middle there, it's still just 1 meter away. When we solve for that, we end up getting 89,900. So it's just one less zero. Newtons per coulomb. All right, so that's how much this Q2 charge is pushing in the opposite direction. So that is the electric field of B. And what we want to know is, well, which direction is this thing moving and with what magnitude? Well, it's obviously pushing it has a stronger electric field from A than it does from B. So it's going to be moving to the right. So my electric net field is going to be moving to the right. Well, with what value? In order to figure that out, we're just going to simply take that 899,000 minus 89,900 to give us a grand total of 809,100 newtons per coulomb, and then we would say it's going to the right. Okay, and that would be your final answer right there. I'm wanting a magnitude and a direction. You can go ahead and try one on your own. So you can try this one on your own for calculating the net electric field. The few differences I made on this one, all right, so that I want you to keep in mind as you try this one on your own, is I have now made Q1 is now a -10 to the -4th. All right, so keep in mind now that's going to be attracting in this direction. And I've also moved, I've created a new point over here called point C. So I want you to figure out what would be the electric field at point C there. And point C is 0.5 meters away from Q. So this distance right here is 0.5, just for a little bit of clarification. Okay, hopefully you get the right answer there. As always, if you have any questions, make sure you email me, let me know. Make sure to finish that exit ticket by 2:30 so you can get your attendance for the day. Have a wonderful day.